Okay, so this is part 2. This is a continuation of my explanation for how to solve linear first-order differential equations. In part 1, I went through what we do, and I showed one example, but I saved a couple more examples for this video. So here we go with another example of a linear first-order differential equation. Notice it's got a dy dx term and a y term, and a term that doesn't involve y. So you got something times dy dx, you got something times y, and then you got something here where all the somethings are functions of x, but they don't involve y. So this is linear. And if I'm going to solve it by the approach we talked about, step 1 is to put it in the form dy dx plus something times y equals something. And it's almost in that form already. All I really have to do is to get rid of the x in front of the dy dx. So I'm going to divide through by that. So everything on both sides gets divided by x. And that gives me dy dx plus 1 over x minus, and then of course 3x over x would just be 3. So we got that times y. And over here we divided through by x, and the x squared divided by x is x. So it's 3x times e to the 3x. Now, do you remember step 2? Step 2 is to find the integrating factor that we have to multiply through by. And that integrating factor we get by finding an antiderivative of the thing in front of the y, the coefficient function that y is being multiplied by, and then taking e to that for the integrating factor. So here that's going to be e to the integral of 1 over x minus 3 dx. So the antiderivative of 1 over x would be ln of x, minus the antiderivative of 3 would be 3x. And so we got e to the ln of x minus 3x. And when you got more than one term in the exponent there, we can split it up like e to the ln of x times e to the minus 3x. And then e to the ln of x would just be x. So this simplifies to x times e to the negative 3x. So that's the integrating factor. Step 3, now that we know what the integrating factor is, we got to multiply everything on both sides by that integrating factor. So we get x times e to the negative 3x times dy dx plus x times e to the negative 3x times 1 over x minus 3 times y equals x times e to the negative 3x times 3x e to the 3x. And if I multiply some things out, if you take x times e to the negative 3x times 1 over x, the x times the 1 over x is just 1, so that part is e to the negative 3x. Meanwhile, we take this times minus 3, and we get minus 3x e to the minus 3x. So we got all of that times y. And over here, this x times this x gives us x squared. This e to the negative 3x times e to the positive 3x is just 1. It's e to the 0, which is 1, or they're reciprocals of one another. So they multiply together to give us 1. And we've also got a 3 here. So this ends up being 3x squared. Now, the left side of this expression, as always when we do this, is made up of the kind of thing you would get by using the product rule on the integrating factor times y. That is, it's the derivative of x e to the negative 3x times y. Because it's x e to the negative 3x times the derivative of y plus y times the derivative of x e to the negative 3x. And of course, in finding the derivative of x e to the negative 3x, we got to use the product rule on that. And it's one thing times the derivative of the other thing, and then the other thing times the derivative of the one thing. Okay, now we're ready for step 4, where we just anti-differentiate both sides. The antiderivative of the derivative is x e to the negative 3x times y. And the antiderivative of 3x squared is x cubed plus c. And here we do want to include the plus c because we are looking for the general solution to this particular differential equation. And that general solution is going to have a constant in it, a constant of integration. So if you really wanted, you could leave it like this. but it would be a little nicer if we got the y by itself, got this solved for y. That's easy enough to do. Just divide through by x e to the negative 3x. And dividing by x, well, dividing by e to the negative 3x would be the same as multiplying by e to the positive 3x. So this might look a little more elegant if we put it as x cubed plus c times e to the 3x over x. And there's things you could do to mess around with that a little, other slightly different forms you could put it in. But there, we're basically done. That is the solution. This time I'm not going to check to make sure it satisfies the differential equation. You can if you want. It gets a little complicated, but it should work in the differential equation if we put this in for y and the derivative of this in for dy dx. But let's try one more example, another differential equation to solve using this method. So this time we're solving y minus x plus xy cotangent x all times dx plus x times dy equals 0. And I notice this is not a separable differential equation. It's not an exact differential equation. We could test for exactness, but it doesn't pass that test. It doesn't have homogeneous coefficients. So of the various methods I've talked about in these videos, the only thing we know how to do is the thing we've been doing lately, treating this as a linear differential equation. Notice there is a y and there's a dy, but the y isn't being squared or being cosigned or being ln'd or anything like that. So I should be able to rearrange this so it really does look like a linear differential equation in the form that we want it to be in. First, instead of having a dx one place and a dy the other place, let's just get it so there's a dy dx someplace. So I'm going to divide through by dx. And then I'm going to shift things around so that the dy dx part is in front, and then come the y terms, and then I'm going to put the terms that don't involve y over on the other side. So x dy dx plus, and then there are two terms that have a y, but if I factor out the y, it's 1 plus, oh, wait a minute, this should be a plus. So there, I went in and fixed that. So we got 1 plus x cotangent x all times y, and then on the other side, we got a positive x because I added x to both sides. And now I don't want anything in front of the dy dx, so I'm going to divide through by x. So I get dy dx plus 1 over x plus cotangent x times y equals 1. So now it is in the form that we want it, and now the next step is to take that equation and find the integrating factor, which is e to the integral or antiderivative of the thing in front of the y with respect to x. So the antiderivative of 1 over x would be ln of x. And for the antiderivative of cotangent x, if you don't remember what that is, you can look it up. It's ln of the sine of x. And so we got e to the ln of x times e to the ln of sine of x. And the e's and the ln's counteract one another, so we get x sine x. That's the integrating factor. So next I will, of course, multiply through by that integrating factor x sine x. So x sine x dy dx plus x sine x times 1 over x minus cotangent x times y equals x sine x times 1. And if I multiply through the x sine x times the 1 over x, the x's cancel, and that's sine x. And if I multiply it times cotangent x, remember cotangent is equal to the cosine over the sine. So if I multiply that times sine, the sine over sine cancels out, and we have just cosine. So here's what we have. X sine x dy dx plus the quantity sine x minus x cosine x times y equals x sine x. And as always, the left side is the derivative of the integrating factor times y, of x sine x times y. If you apply the product rule to that, you get the first thing times the derivative of the second thing, so x sine x times the derivative of y, plus you get the second thing times the derivative of the first thing. So y is getting multiplied by the derivative of x sine x. And using the product rule on that, we get, oh, and I should have changed left those minuses as pluses. Remember, I had that thing that I fixed. So there we go. I updated this to match my earlier correction where I had a minus where I should have had a plus. Now, we're ready for step 4, where we anti-differentiate both sides. So, of course, the antiderivative of the derivative of x sine x times y is x sine x times y. And for the antiderivative of x sine x, well, to work that out, you would either use integration by parts, or you would just look it up on a table of integrals, and you would find that the integral or the antiderivative of x times the sine of x turns out to be the sine of x minus x times the cosine of x plus c. So we're essentially done. If we want this solved for y, just divide through on both sides by x sine x. And that simplifies to y equals 1 over x minus cosine over sine, which is cotangent of x, plus c over x times, and I can write 1 over sine as cosecant of x. So that's the end of this video. Now you've seen how to solve linear differential equations of order 1.